Oh, we had it easy.
Alright, so at the beginning of the year I told you there were 3 main topics in calculus, and so far we've covered 2 of the 3. What are the 2 we've covered?
Derivatives.
Derivatives?
Second derivatives. Slow as an engine light.
What was before derivatives?
Limits.
Limits. So we've done limits and derivatives, and now we're moving on to integration. Okay, here's what we're looking at today, is integration. So we've got from now to about spring break to get integration covered. Because hopefully when we come back from spring break, all we'll be doing is reviewing really
It's like the first year, that's what we get.
and we may be doing a few things after spring break, but we'll be able to review for 3 to 4 weeks and get ready to go for the test. Say it again.
It's going to take until spring break for it on this.
There's a lot, yes.
Spring break.
I was looking at
May, like the first or second Wednesday in May. Alright, so when I take the derivative of something, such as if I want to take the derivative of f of x, what does that give me? It gives me f prime of x. When I take the derivative of f prime of x, what does that give me? That gives me f double prime of x. Okay? And that is called differentiation. What we are starting on today is integration. But another term for integration is called anti-differentiation. So, what does the prefix anti mean?
No.
What'd you say?
Against.
Opposite. So it is the opposite. So integration is the opposite of differentiation. There you go. That's exactly what we're doing. Okay? So instead of going from f of x to f prime of x, we're going to be going from f prime of x to f of x. So derivatives take us down and integration takes us back up. So that's what integration does for us. It allows us to go back up the ladder. Okay?
Integration takes us to the top.
Yes.
When we do integration, is it going to go over what to do for constants that are in the f
Yes. Okay. Now the symbol for integration, you've got your symbol up here. That right there represents we want to take the derivative of something. The symbol for integration, as you'll see on that paper, is that symbol right there. So for instance, if I wanted the integral of f prime of x dx, what should that give me? F of x? That should give me f of x. Logan, why does that give me f of x? Because integration helps me go up a function. So if I'm at the function f prime of x and I integrate it, I end up at the function f of x. Yes.
Does that thing have a name, or do we just call it the integration style?
This right here is called integral. Okay.
So it's gigantic I.
It is closer. It is closer to an S, and the reason why it's an S is because, as you'll see later on today, the S stands for sum, and you'll understand a little bit later today why it stands for sum or why S.
Say
Say it again.
Are we going to have to do sigma stuff again?
We're not going to have to do it, but we'll talk. And sigma is related to this.
I know the S doesn't stand for sigma.
Okay. Now there are 2 different types. There are 2 different types of integrals. There is an indefinite integral. Indefinite integral and a definite integral. Alright, and today we're going to be mainly focusing on the definite integral.
We're focusing on definite.
Looking at definite today. Okay, here's the difference between the 2. An indefinite integral looks something like that, and a definite integral looks something like that. That's the difference between the 2. A definite integral will have numbers on the S, an indefinite integral will not have numbers on the S.
What's the dx?
the dx, that tells me just like when I had d over dx, what did the dx tell me here?
In respect to
In respect.
We're doing it with respect to x. Same thing here. The dx here tells me I'm integrating with respect to x. Okay, that's one way to think about it. We'll talk about. There's a lot to it. There's a lot of things that. There's a lot of meanings in this that we'll get to later. You can't handle it today though.
Okay. Okay.
All right. So we go back to this thing right here, the definite interval. There are two main things that this thing represents that we want to take away today. Okay, and anytime you see a definite integral, you need to be thinking about these two things that it represents. Okay, the first one is it represents the change in the function above over the interval. So it represents the change in the function above over the interval. Now, what would my interval be? A to B. So my interval, that's where these numbers come in. That's the interval. So it is the change in the function above over the interval. Okay, that's the first thing it represents. The second thing it represents is the area under the curve of the function. Over the interval. It's the area under the curve of the function over the interval. Those are the two things. Anytime I see a definite integral, those are the two things I need to think about. And if I can think about those, that makes understanding what to do a lot simpler, and I'm going to be able to answer questions a lot better. When I see a definite integral, I need to know it's the change in the function above, and it also represents the area under the curve. Okay? And we're going to be dealing with both of these things today on the problems we deal with. All right, now I know that's a lot, and you may not understand anything, but there anything I can clear up before we move on, and it's not imperative that you understand everything I've done today. Okay? This right here is the main thing we need to understand so far. This represents two different things. Change in the function above, area under the curve. Those are the two things we need to know so far. Okay? All right, so let's look at, on our sheet, let's look at some problems here. So let's look at number one. All right, these are free response questions, and most of the time, what we're doing today will show up in a free response question. It pretty much shows up every year, and if you can handle it, you're talking about 3 to 4 points on the AP test. Okay. So today, the main thing we want to do is we're going to use Riemann sums to approximate definite integrals. Okay. So we want to use Riemann sums to approximate definite integrals. So let's read this whole thing, and then we'll get into what we're going to be doing today. So it says the volume of a spherical hot air balloon expands as the air inside the balloon is heated. The radius of a balloon in feet is modeled by a twice differentiable function r of t, where t is measured in minutes. Between 0 and 12, the graph of r is concave down. So what does that tell me? If r is concave down, what else does that tell me?
decrease.
F line is, or F is decreasing.
We're dealing with r.
Okay.
So if r is concave down,
F prime of x is decreasing.
R double
Where-
prime is decreasing.
r prime of x is decreasing, and r double prime is
Negative.
negative.
Something.
Okay.
I was doing
The table above gives values of the rate of change r prime of t of the radius of the balloon over the time interval from 0 to 12. The radius of the balloon is 30 feet when t equals 5. Now, what did we say r is concave down means? R prime is decreasing. Does this show me that r prime is decreasing?
Yes.
Yes. Okay, so that's something good there. So let's answer the question. It says use a right Riemann sum with 5 subintervals indicated by the data to approximate this definite integral right there. Now, what are the two things we said a definite integral represents? Changing the function above or
Area under the curve.
area under the curve.
Does it not represent both or just one or the other?
It represents both. Okay? So it's the change in the function above, and it is also the area under the curve. Okay? But usually when we want to approximate it, we're looking at the area under the curve. Okay? And the change in the function above part is going to come in when it says we want to explain the meaning. So the change in the function above, usually that's where you use it to explain the meaning. The area is where you use it to find the actual value. Okay? So I want to approximate this. And to do that, we said that represents the area under the curve of r prime of t. So to get started, what I want to do is I just want to plot this information to kind of give me a visual of what it is we're looking at. So this first time we're going to plot it, and then we should be able to do this stuff without plotting it. We should be able to do it without having a visual. So all right, so we're going from 0 to 12. So at 0, I'm at 5.7. So we'll call that 5.7. So there's 0, I'm at 5.7. At 2, I'm at 4. So 2, we're going to say this is 4 right here. And then at 5, 3, 4, 5. At 5, I am at, what did I say? At 2, I was at 4. At 5, I'm at 2. Then we're going to 7. So at 7, I'm at 1.2, so somewhere in there. At 11, 8, 9, 10, 11, I'm at 0.6. And 12, I'm at 0.5. So that is the information they've given me. So I've got some curve that is connecting all of these dots. Okay? And we said this definite integral right here represents what? The area under this curve. So it is, we're talking about the area under this curve right here. Okay? And one way we approximate this area, and that's where the Riemann sum comes into play. When you're doing a Riemann sum, you're going to approximate the area using two types of figures. It's either going to be a rectangle or it's going to be a trapezoid. Okay? So, if it wants you to do a trapezoid, it's going to say trapezoid. So if it doesn't say trapezoid, you know you're going to be finding an area using what? A rectangle. Okay? So, and there are three different types of rectangles. In this case, it wants a right. So there's going to be a right, there's going to be a left, and there's going to be a midpoint. Those are the three different types of rectangles you're going to have to find. So we've got those three plus the trapezoid. That's what we're going to use to approximate area under the curve. Now, so in this case, I want a right Riemann sum. So what did we say we were using to, what figure are we using? We're using a rectangle. So with each one of these marks they have given me, 0 to 2, I'm going to draw a rectangle. 2 to 5, there's going to be a rectangle. 5 to 7, I'm going to have a rectangle. 7 to 11, and then 11 to 12. What do you think they're telling me on the right? What the right, the midpoint, or the left? What does that do to my rectangle? And if you don't get it, if nobody, I mean, you're kind of reading my mind right now, or trying to. Any idea of what the right, left, or the midpoint is telling you to do with your rectangle? What it tells you is, that tells you which side of the rectangle to go up on. Okay, so since it's a right rectangle, on this first one right here, there's my rectangle, and since it's a right rectangle, they want me to go up on the right side. So if I go up on the right side, I'm going to hit that spot right there, and that's going to be the top of my rectangle. So that tells you which side to go up on. If it was the left side, if it was a left Riemann sum, I would have gone up on the left, and the top of my rectangle would have been there. Okay? And the midpoint, I would go up on the midpoint, and the top of my rectangle would be somewhere in there. So the right, left, or midpoint tells you where to go up to get the top of your rectangle. Okay? So here's my first one. My next one, I'm going to go up on the 5 and go over. I go up on the 7 and go over. I go up on the 11 and go over, and then I've got my last one. So that's where my rectangles come from. So now I just need to find out the area of each one of those rectangles and then add them up. So what do we use to find the area of a rectangle? Length times width. So on this first one, what's my width? 2. Now the length is going to be the height of it. So what's the height of this first rectangle? 4. Okay. On the second one, what's the width of it? 3. And what's the height of it? 2. The next one, what's the width? 2. What's the height? 1.2. The next one, what's the width? 4. What's the height? 0.6. And the last one, what's the width? 1. And the height? 0.5. So I've got everything I need to give me the area of each one of those rectangles and add them up. So if I do that, alright, so I need 8 plus 6 plus 2.4 plus 2.4 plus 1 point, or what would that be, 0.5? So that gives me 19.3. So 0 to 12, r prime of t dt is approximately 19.3. Now, what about my units on that 19.3? What would my units be and why? What is it? Feet per minute? No. It's just feet.
Oh.
Pauline, why is it just feet?
Because you're going back up from the derivative. So I just figured it was just feet.
Okay, so when we take the derivative, what happens to our units as we take the derivative and we go down? We add a unit, right? So if I'm going the other direction, what's going to happen? I'm going to take away a unit. So r prime of t is feet per minute. So if I take a unit away from feet per minute, I end up at feet. Okay, so that's one way to think about
Since it's an area, doesn't mean it's square.
it. It doesn't. Okay. All right. Now, the next thing it says is use the correct units to explain what this thing means. Okay. Now, we just figured out the area under the curve of this thing. So, what am I going to use to explain the meaning?
Change in the function.
I need the change in the function above over the interval. Okay, so we're going to start with that. So it is the change. The change in what? Which is what?
Feet.
No, what's the function above r prime of t? R of t. So the change in r of t. Okay, and then what?
Over the 0 to 12.
Okay, so from t equals 0 to 12. Okay, now we've got to clean that up a little bit, but I wanted you to start with that. Okay, that's always a good place to start with. Now, we've got to replace some words here though. We never want to end with change. There are 2 types of change. What 2 types of change are there? No, that's not what I'm thinking of. Get it in my mind.
Read your mind.
Positive.
What is a positive change? Increase or decrease. So there are 2 types of change. So most of the time we want to take this change out and we want to put increase or decrease. So in this case, what's it going to be? It's going to be an increase. Why is it an increase?
It's positive.
Because this is positive. So we're going to say it's an increase in what? What does R of t represent?
Feet.
Minutes.
What function does R of t represent?
It's the volume of the balloon.
Radius.
It's the radius.
Over time.
So it's the increase in the radius. And you have to give me the units of the radius. What are the units of the radius? Feet. So increase in the radius in feet. And then you have to tell me from t equals 0. What are my units on 0 though? Minutes. To t equals 12 minutes. You've got to have units everywhere. If you don't have units everywhere, then it's going to be automatically wrong. And usually that statement right there is worth 1 point. Okay? But you've got to have, you need to tell me that it's an increase or a decrease. You've got to tell me an increase or decrease in what. And then you've got to tell me the time interval it happens in. Okay? Now, I want to go back and do this problem, but I want to do it without drawing it. Okay, so I want to approximate this thing without drawing it. So, what 2 things do we need? What did you say?
The chart.
We need the chart, yeah. To find the area of the rectangle, what do we need is what I'm asking.
Oh, like
I need the width and I need the height. Okay? So, I'm going from 0 to 2, 2 to 5, 5 to 7, 7 to 11, and 11 to 12. So, what is my first width? 2. And what is my first height? 4. Now, why did I choose 4 over 5.7? Because it is a right Riemann sum, so we want to choose the right value. Okay? What's the width of the next one? 3. And the right value is 2. What's the width of the next one? 2. And the right value is 1.2. The next one? What's the width? 4. And the height? 0.6. And the last one is 1. And the height is 0.5.
So if we did midpoint without a chart, we would have to take.
No. If it's a mid, we'll get to midpoint. Yes.
So is either way acceptable on the AP test, or is this preferred?
No, this is what we want to do.
Okay.
Okay? If you need to draw it, then draw it. But this is the quickest way to do it. So, this one right here gives me the right Riemann sum. What would be the difference if I wanted the left Riemann sum?
You go
I would choose the left values instead of the right values for my height. That's the only difference.
Would we wouldn't use, if we're using a left Riemann sum, we wouldn't use 0.5 as a.
Correct. If you're using a left Riemann sum, you won't use the last number. If you're using the right Riemann sum, you won't use the first number. Very good. All right, let's look at the next example.
So using the middle one, use all of them?
No, we'll get to the middle one. We got a middle one on the next one.
Oh. Got it into.
No, they're going to give you some more information if they're willing midpoint. All right, so number 2 says rocket A has positive velocity. What does it mean to have a positive velocity?
Go in the right direction.
Increasing
Increasing your
your
speed.
The function above is increasing. Okay, so if velocity is positive, that means my position is increasing. Okay, and does my chart match the fact that they said my velocity is positive? Well, never mind. I'm thinking of something else. X that out. All right. After being launched upward from an initial height of 0 feet at time t equals 0 seconds, the velocity of the rocket is recorded for selected values of t over the interval from 0 to 80 seconds, as shown in the table above. First thing it wants is, using correct units, explain the meaning of that in terms of the rocket's flight. So, if I'm going to explain what that thing means, what is it I want to be thinking about?
That
Yeah. No.
function above.
What about the function above?
Change.
All right. So right now, I want to start by writing down. I want to start by writing down change in which function are we talking about?
VFT.
No.
No, of course not.
What?
Is it just velocity thing?
V.
Just
prime
of t.
V, just V.
Just v.
Not V of t, but V.
T.
V of x.
What did we say this thing represents? The change in what?
Oh.
The function above. What's the function above velocity?
Position.
Position.
Oh,
A change in position
oh, that's on me. I knew that. Gotcha.
from
Why do you always
t equals 10 to t equals 70. So that's my initial. Now I want to go back and clean it up. What do we want to replace change with?
Increase or decrease?
Increase or decrease? So what's it going to be? It's an increase. How do we know it's an increase?
greater than 0?
Because velocity is positive.
Because velocity is positive. That's how I know it's an increase. So an increase in position. Can't spell today. Getting excited. In position of what?
In feet.
It is in feet, but what else is it? Position of what?
The rocket.
Position of the rocket
Nice. Nice.
in feet from t equals 10 what?
Seconds.
Seconds to t equals 70 seconds.
We have to write out feet, or can we just put FT?
You can put FT.
Okay. Those two easy. Two.
Okay, now if you like writing this down first and then interpreting into that, that's great. If you want to go straight to this, that's fine as well. But if you're on the AP test and you write this first, then after you write it down and after you adjust it, then mark it out, because if you have something X out, they're not allowed to look at it if you have it X'd out. So if you write it and then you get to what you want to say, then just go back out and X out up here. Don't erase it, just X it out. Because they're not allowed to look at anything that's X'd out. Alright, so now it says use a midpoint sum with 3 subintervals of equal length to approximate my definite integral from 10 to 70 of v of t.
Why does this say 80?
Let's get
Say it again.
Are we not on B?
We're still on eight.
We're still on A.
My bad.
The second part of that.
I didn't really-
Okay, so we want to use a midpoint Riemann sum with 3 subintervals of equal length to approximate that integral. Now, here's the trick on a midpoint Riemann sum. If they're giving you a midpoint Riemann sum, that means when you choose your interval, there needs to be 3 x values in each interval. Okay? So instead of, we're starting at 10, instead of going from 10 to 20, we want to go from 10 to 30. Why do we want to do that?
So what you know what the midpoint.
So there is a number in the middle. So that's what's going on with the midpoint Riemann sum. You're always going to have a width of 3 values, and then you're going to have something in the middle. So that means I'm going from 10 to 30,
Yeah, it does.
then I'm going from 30 to 50, and then from 50 to 70. So that's the trick on a midpoint. You're going to have 3 values in an interval.
Is there ever going to be a situation where if you try to go to the third one, it doesn't work out? Like you don't get to the last number?
No,
correctly?
it should work just like this.
Alright. Just so.
Okay. But again, since it's a midpoint Riemann sum, what is my figure going to be again? It's still a rectangle because it didn't say trapezoid, so it's still a rectangle. So I still need to know how wide is it. So on my first interval, how wide is my first interval? 20. Okay, and then which y value do I use for its height?
22.
22. You use the one in the middle. Okay, how wide is the next one?
20.
It's also 20. How tall is it?
35.
35. Okay, how wide is the next one? 20. And how tall is it? 44. So when I punch that in, I should have that one somewhere in here, I think. 25, yeah. I get 2020. Now, what would my units be on 2020? Feet. Logan, y feet. We want, it's the function above, so the function above velocity is position. The units for position in this case would be feet. What's another way to think about it?
Subtract
I lose a unit. So since I'm integrating velocity, and velocity is feet per second, that means I use a unit. I eliminate the second, and I end up with feet. Okay, but then you can also go back to your explanation that you wrote,
This guy.
and because what did we say this represented?
Rocket.
Yeah, what did we say?
Position of rocket.
The increase in position of the rocket in feet. So that we already decided what this was going to be in. Okay. All right, now
I feel like I'm getting really excited.
I am part B. I'm really going to be pumped about part B if we can nail part B. Part B brings in some stuff we learned back in
Average.
the first semester. Okay, so we want to find the average acceleration, as Brock says, of rocket A over the time interval from 0 to 80 seconds. So Brock, what am I going to do?
Change in velocity. No.
Yes.
Change velocity over change in time.
Change in velocity over the change in time. Very good, Brock. So it is v of 80 minus v of 0 over 80 minus 0. Because when I see average something, it represents what? The change in the function above over the change in time. So what is v of 80 in this case? 49. What's v of 0? 5 over 80. So we end up with 44 over 80. Now it says indicate units of measure. So what would my units of measure be for 44 over 80?
Feet per second squared.
Feet per second squared. Why, Brock?
Because you didn't like feet per second.
Because it's now
Yeah, just read this right here.
acceleration.
Average acceleration. What's the units for acceleration? It's got to be something over a time squared. So that's why it had to be feet per second squared. Now, what is something else? What is something else that represents v of 80 minus v of 0 that we've done today? What else is equal to v of 80 minus v of 0?
A rock. A rock.
No.
V of 60.
49. No.
Now let's go back to average acceleration. If I want to find the average of something, what do I need?
Function above,
What about the function above?
the change.
So how can I represent the change in the function above?
With the little S.
Right. If I want to do from 0 to 80 of what function? A of t dt. That right there is the same thing as v of 80 minus v of 0. Okay? Because this is equal to that. Okay? And we'll need that going into the last example we had.
What didn't you believe?
All right, number 3.
Whenever you do a rock.
Number 3, we have a metal wire of length 8 centimeters is heated at one end. The table above gives selected values of the temperature in degrees Celsius for the wire x centimeters from the heated end. The function t is decreasing and twice differentiable.
Wow.
So what does it mean if the function t is decreasing? What else does it tell me? No.
The derivative is negative.
The derivative is negative. Very good, Chelsea. Okay. All right. It says write an integral expression in terms of t of x for the average temperature of the wire. And we're going to stop right there, and we should, that right there should be blinking at us. Average temperature. How do I find average temperature?
Change in function above.
Change in the function above over
Change in time.
the change in time. Now, how do I get the change in the function above temperature?
Integration.
Integrate. Integral.
So what would that look like?
Zero.
0 to 8 of t of x
Yeah.
dx. So what does this right here represent?
The average temperature.
No, that represents the change in the function above temperature. And this down here represents what?
Change in time.
The change in time. Okay, so it's always the change in the function above over the change in time when you're wanting average of something. When do I want the f of b minus f of a or b minus a? What key words?
Of change.
Of change. When you see of change, that tells you want an f of b minus f of a or b minus a. Alright, so there's the first part. Write an integral expression in terms of t of x, which we have done. Now it says estimate the average temperature of the wire using a trapezoidal sum with 4 subintervals indicated by the data in the table. So now we need to estimate it using a trapezoidal sum. So now I'm dealing with trapezoids. So we need to know what is the area formula for a trapezoid.
Is like
1/2
Base.
times the height,
Ah.
base 1 plus base 2.
Oh, that's so simple.
Now, you guys are probably used to a trapezoid looking like that, to where your bases are on the top and on the bottom. Okay? But when we do Riemann sums, our bases are not like that. Or our trapezoids do not look like that. Our trapezoids look something like that.
so they're
Okay? So that means the height is actually going to be what?
The original basis.
The distance between my x values. That's just going to be the same thing as the width we used on the rectangle. Okay? Now, these bases, where do we get the bases from? The 2y values. So what do I have to do with my 2y values?
subtract, add.
I've got to add my 2y values together. So I'm going to go 1/2 times however wide my interval is, and then times my 2 bases added together.
So H represents the width.
H represents, the width in this case. Okay, so 1/2 times the width of the interval, and then times my 2 bases added together is what we're going to do. So, this is what I'm interested in right now. So on my first one, I have 1/2, and how many intervals? It wanted 4, so let's see. 1, 2, 3, 4. So there's my 4. So how wide is the first one? How wide is the first one? 1. What are my 2 bases? 93 and 100. So if I add those together, I get 193. Then I need 1/2. How wide is the next one? 4. My 2 bases added together. 163. And I've got 1/2. How wide's the next one? 1. My 2 bases. 132. And I've got 1 more. How wide is it? 2. And my 2 bases. 117. Now, what do you notice each one of these has? A 1/2. So if I'm doing this, and I'm you, I'm going to take the 1/2 out, and then worry about everything else.
So the 1/2 is completely pointless.
So I'm going to do 193. Whoops. I'm going to do 193 plus 4 times 163 plus 132 plus 2 times 117, which gives me 12, 11. Then I'm going to divide that by 2. And that gives me 605.5. Now, what does that 605.5 represent? The change in the function above. So this right here is just the top part. But I want the average temperature, so what do I need to do to 605.5 to get the average temperature? I divide by 8. So then I divide that by 8, and that gives me 75.687. And what do my units need to be on that?
Celsius.
It needs to be degrees Celsius. Now at this point you need to ask yourself, does my answer make sense? Because what is it we're trying to find? We're trying to find average temperature.
Yes.
So
Look at the temperatures I have. 100, 93, 70, 62, 75. Could this be the average temperature? Yes. So always make sure of this, because here's what happens on this particular problem. And I did it with the first hour, or the first class. Is a lot of people will get that right there and they'll say, that's my answer right there. This is 605.5 degrees Celsius. That's my answer.
That's hot.
But does that make sense? No. And a lot of people forget that part right there. Okay. Because of that, there is a point just for finding this number, and then there is a final point for dividing by this. Okay? So in this particular problem, there's probably 3.2. There's probably a point for setting it up, there's a point for finding that value, and there's a point for finding that value. So that's 3 points more than likely, unless they give me a fourth because I used the correct units. So that's what's going on that. Okay? So there's a quick intro to integration. And a definite integral represents two things. What two things does definite integral represent?
The area under the curve.
Area of the curve or the change of the function above. Okay? And if I want average of something, what do I need? Change of the function above over change in time.
So that's on my level.
Very nice.
Good job, Brock. Proud of you.